now we will move to the next presentation on Desire-6G. So Gergely, I hope I pronounce correctly your name. The floor is yours.
Thank you. Well, not exactly, but it's a very hard name. It's Hungarian, so it's no problem at all. It's
how do you pronounce it?
It's Gergely. Ly in Hungarian is J, basically. So it's hard to understand for somebody no Hungarian. I accept. No problem. So basically, I have a few slides on Desire-6G and specifically on the system architecture. So I'm not really prepared with the bureaucratic details of the project itself, but I will try to dig in to the architecture and why we are doing this, and these ideas are where the main ideas that we center research around. So just a brief overview then. So as you can see on the right, Desire-6G has quite some members all around the EU basically, and also one from Israel, with some big industrial partners like NVIDIA, NEC and Ericsson, Telefonica as a vendor basically, a couple of universities, and a few SMOs as well. And the main argument that Desire-6G is studying basically is twofold: deprogrammability and this secure distributed intelligence. So these are the two main technologies, I would say, and the goal is to have a very flexible network that is capable of supporting real-time end-to-end use cases, basically in a 6G context. And the project leader is the University of Amsterdam, and the technology leadership is at Ericsson, Hungary. So I'm the technical coordinator of the project. And the key innovations you can see here, but I will just move through the animations because we kind of have 4 basic layers, or basically, well, 3, but we think that this privacy preserving monitoring layer on the bottom is quite important. It deserves its own box, but it's actually part of the deep data frame programmability layer, having probes all around, kind of deployed flexibly, and also the functionality can be programmed for the monitoring as well. Also for the data plane or the user plane. Recently, I heard that especially Chinese vendors are starting to use data plane as an AI terminology, basically. Here, if you see data plane, still the old-fashioned data plane, so when we move packets in and out. So it's more like switching routing and this network-specific data plane, I would say. Then on the top, we have the optimization layer. The first part is the multi-agent-based network management and control layer, which does optimizations as well. And on the top, we have the intent-based orchestration and service management layer, which is in charge for deploying different services and slices. I mean, for us, services and slices are pretty much the same. This is the architecture, I would say, detailed picture. I think I won't go into the details for the sake of time, but you can see the basic layers on the right. So I think it's enough if you just see that, like, we have these 3 basic layers, plus of course we have the physical infrastructure that is running pretty much all functions for us. And how we actually use that physical infrastructure is what where we can probably make a difference by hiding the details layer by layer, I would say. But I will come back with an example. But first, just to mention that in Desire-6G, we consider all sites that has some compute and hardware resources as Desire-6G sites. But those could be quite different. So, for example, we can have like a far edge run site with the necessary run hardware entities and whatever is needed there basically. And of course we can have like core or cloud sites as well, where I would say CPU resources are probably dominating, maybe some GPU resources for those type of workloads, and probably less specialized hardware is needed in those sites. But of course, we could have hardware accelerators there as well, especially in the infrastructure layer, which can be programmed. If they can be programmed, then we can, of course, use them as part of the Desire-6G framework. I will show how you can do that in a moment. So I guess this, so this is basically a slide that talks about many things. First, I have to talk about the service itself. So what is a service for Desire-6G? In Desire-6G, a service is pretty similar to a slice that we call, like in the telecom industry, we call it probably a slice. The main difference probably is that it's a bit more widely used than traditional slices. But we think that if the setup of these services could be quite dynamic, I would say, and quite fast, that could lead us to an architecture where the different use cases could be quite well supported in a multi-service environment, without actually having to kind of optimize your generic architecture to specific services. And basically, in a nutshell, the idea is that on the top level, you have this high level, maybe intent-based service creation. So you just describe your service as a bunch of network functions, basically, and they can be either in a chain or a graph. It doesn't really matter. So mostly we use network graph. In this example picture, you can only see a network chain, and on the top you just kind of specify the behavior. So the kind of the business logic of your network. So what it does with the user's packet, basically from A to B. And the start and end could be either like basically it can be end to end. So we can kind of enhance or kind of move the Desire-6G concept or the site concept to the user equipment itself, because that's also a compute device to some extent. So in that sense, we can have kind of end-to-end services where the service, the parameters or the KPIs of the service can be monitored basically end-to-end. That can be kind of optimized end-to-end. But we do have the traditional services as well in the system, when the start and the end is pretty much inside the mobile operator's domain. So most likely start is a run site where the user equipments are joining the radio network, and the end is most likely a core network site where the traffic leaves the core network. Then if we, after having this high-level logical view, we are starting with site allocation. So that's the job of the SMO, to actually see which sites are needed, usually multiple sites or multiple sites for the run part, most likely, and maybe a few core sites, maybe some intermediate sites. In this simple example, we only have two sites. And then after having that, the SMO translates this or transfers this information to the infrastructure management layer, the IML, which will populate the infrastructure network functions, for example, load balancers, router switch adapters to move traffic between the sites, heavy hitter logic, etc., etc. So there are these, so to say, cloud native helper functions that are added transparently, basically, by the infrastructure management layer. And then at the end of the day, we will have a physical mapping again, is done by the IML and also by the help of the Vim, which in our case is basically Kubernetes. And then we have the physical view can be like this, that we have a bunch of x86 servers on this can be a small site or maybe a run site, and maybe a programmable hardware, a switch like a Tofino, and then those functionalities could be distributed among these hardware resources. And then how this distribution goes and to which hardware element the actual worker runs, it's not an information that is needed by the top level, so by the SMO or by somebody else. It's simply hidden by the IML on the given site. This is how we can make this like a bit more cloud native than the current user plane is. And then on the top of this, we have the three optimization layers, I would say. We have local optimizations, which are kind of domain specific, I would say. But in our domain, in the cloud infra domain or the Desire-6G infrastructure domain, we have the IML, as I mentioned, that can do some optimizations. I will come back to this. And this is quite fast. So we are in the millisecond timescale here. And okay, and yeah, and I didn't even mention the traffic management, where we have some traffic management inventions as well, which is on the packet level, so it's way below the millisecond level. And then on the top, we have the service optimizations with the multi-agent system, which can have different agents, and it can optimize the service itself in an end-to-end fashion, but it sees basically one service out of the many services. If there is a problem that even the MAS that can see all sites and that are used by that service cannot do or cannot optimize, then we are up to the SMO layer, and then the SMO layer can understand basically each and every services, each and every sites, so it can do partial or full redeployments if the problem is too big for the MAS to solve. Okay, I think I still have some time, so let's talk a bit about the programmable data plane and what do we do there to achieve transparency and transparent acceleration and optimization. So as I said, the key guy here is the infrastructure management layer, the IML, that will do the optimizations and that will hide the details from the upper layers. In our case, the network function, as you can probably envision, a network function can have a data plane entity, a data plane element, and control plane endpoints, basically, or control plane elements. This is pretty similar to the traditional SDN approach, where you have a control plane part and the data plane part. But between those guys, we have the infrastructure management layer that will take care of the underlying data plane entities and their optimization and their scaling and failover and everything, basically. So the control plane can, it can freely work on the logical setup of the data plane. So it doesn't need to see the actual physical workers or hardware entities or whatever that the data plane runs on. It can deal with the logic that it has to do. And how it is done, basically, you can see it on this picture. So on the left, you can see what is the logical view. So then the control plane through the P4 runtime, which is, I would say, in our case, we are using P4 as the language for describing most of our data plane entities. But the P4 runtime is actually a more generic API or interface. It can be used for other data plane entities as well, not just the ones which are programmed in P4. So basically, through this channel, it configures the data plane. It sees that it controls basically one big data plane entity. And what happens in reality, you can see it on the right. So the P4 runtime interface is terminated in the IML. It has basically a proxy that terminates the control plane interface. And below this IML layer, you can have several optimizations. On this figure, we show the heavy hitter and the load balancing as data plane optimizations. And that means that, so heavy hitter means that if you have a hardware and a software entity of the same network function instance, then you can, and typically that means that in the hardware entity, you have less memory, but higher capacity, like in a Tofino environment, for example, that is typically memory limited and not packet per second limited. So you might want to put your heavy hitter users or flows to the hardware devices while keeping the bulk of the users, which are not producing too much traffic on the CPUs. That is exactly what the heavy hitter offload does. And after the heavy hitter offload, you can still go through a load balancer, which will select the appropriate software instance, the software worker, basically for that specific flow or user. And this entire thing is transparent basically to the control plane. So the control plane still talks to one logical data plane entity. And this is how we kind of make it transparent and make it simple. So this is an abstraction level. So for the control plane, the abstraction level is basically the NFDP itself. And basically that was all from my side. So I think I wanted to highlight these optimizations and also the rapid service deployment. So how we actually want to deploy services in the system and how we want to make sure that those services are optimally deployed, and after that, during the lifetime, also kept optimal. Thank you. Open for questions if there are any. Let's check the.
Yes, you've got 2 questions in the chat, so you have time to answer.
Yes. Okay. First question is I guess the P4 software switches. Yes, we are using software and hardware switches as well. Unfortunately, Intel will stop the Tofino line, so the Tofino hardware is, I will say, cease to exist, which is, I think, a pity, but Intel is not in a fairly good shape. So, of course, most likely they have their reasons. And then regarding local optimization, I guess you do not consider the case of previous session reconfiguration modification. Yes, it is correct. Although the multi-agent system, the run specific domain specific mass can kind of indicate reconfigurations or can ask reconfigurations, but in that case, you are right. We are probably in a slightly higher optimization circle. So not 100 milliseconds, but a couple of 100 milliseconds. I think we are still below 1 second in that case. And okay, so I think so the rest of the questions were for the previous presentations, it seemed. Then I think no more questions.
Thank you very much.
And one more question on the intent-based. Sorry, why do we need intent-based? I think that is mainly for simplifying the interaction with whoever uses the system. So in our case, I think the services will be. So we will have much more services than today. For example, T-Mobile have basically introduced 2 slices, as I understood, and they are using this for some quality of service differentiation reasons. But those are just 2. So like we are hoping to have much more services in the system, fine-tuned for different use cases. And in that case, I think the API matters a lot. What will be the API towards the end users, towards the user equipments? I think that matters a lot, and in that case, it cannot be very complex. So that is, I think, where intent-based can help.
Okay, thank you.
Thank you.
Thank you a lot. So now we can move to the projects that deal with communication infrastructure, technology, and device. So now we will have the presentation from Acer project. So Konstantinos, if you can share your slide now.